Hello students, in our today's lecture we will study topic number 1.11.2, physical significance of a dipole. Now here it is given that in the molecules like H2, CO2, O2, CH2, the centers of positive and negative charge, they are not separated, they are at a same place, and hence the distance between these two positive and negative charge will be nearly zero, and hence for such type of molecules the dipole moment P will be zero. So such type of molecules whose dipole moment is zero are called non-polar molecules, while in some molecules like H2O, HCl, etc., the centers of positive and negative charges, they are not at same place, means they do not coincide. In such case they have a dipole moment. The dipole moment is not zero in this case, they have some dipole moment, and so here given that P dipole moment is not equal to 0, means it has some value, and such type of molecules, they are called polar molecules. Like we know that HCl, we can write HCl as H plus and Cl minus. So these two ions, positive and negative, they are separated by some distance, and so they have a dipole moment. Now in our last lecture we have solved example number 1.10. Let us see once again, because this is an important example. Now here it is given that for an electric dipole the charge is 10 microcoulomb and the distance between the two charge, which is represented symbolically twice of a, is 5 mm, and we want to find the electric field on the axis of a dipole as well as on the equator, and we want to find that electric field which is at a distance r is equal to 15 centimeter from the center of a dipole. And we know that for a dipole, if this is negative charge, this is positive charge, then this distance is twice of a, and this is the axis of a dipole, and the line perpendicular to the axis is equator. Now here one thing is very important, that the distance between the two charge, now here one thing is very important, that the distance given, now here you can see that the distance between the two charge is very much small compared to the distance where the electric field is to be obtained. This is in mm and this is in centimeter. So here the condition is r is very greater than a. So in such type of condition we have to use the simple formula for the electric field, and we have studied in the theory part that on axis the electric field is given by this formula. E is equal to 2 kp by r cube. So now we have written this formula for the axis. Also, the electric field on the equator is given by this formula. This also we have derived in the theory part. Now you can see, compared to the electric field on the axis, the electric field on the equator is half. You can see here there is twice of kp by r cube, and here it is simply kp by r cube. So once we are able to obtain the electric field on the axis, then simply we have to make half of the electric field on the axis and we'll get the electric field of the equator. So first we will find the electric field on the axis. Now using this equation and putting the given values and solving, we will get this answer for axis. Here this is 2, this is value of k, this is value of p. Now we know that p is equal to twice of a into q. You can see here p is equal to 2aq. And what is 2a? It is 5 mm, and so we will convert that mm into meter, and the charge is given 10 microcoulomb, so it is 10 into 10 raised to minus 6. And the distance where the electric field is to be obtained, that is r is given 15 centimeter, and so we have to convert that centimeter to meter. So 15 into 10 raised to minus 2, and there is cube, so here also we have put cube. Now calculating, we'll get the electric field on the axis as 2.6 into 10 raised to 5 Newton per coulomb. Now to find the electric field on the equator, simply we have to make half of this value. So half of electric field on the axis, this is the electric field for the axis, and its half will give you the electric field on the equator. So this is about the example 1.10. Now our next topic is topic number 1.12, dipole in a uniform external field. This theory is many times asked in board exams, so it is very important. Now you can see here a dipole is there, a negative charge, a positive charge, and this is the distance between them. Here this dipole is kept in a uniform electric field, and that is shown by this arrow. So this whole dipole is in a electric field E. Also in figure it is given that the direction of dipole moment is this, and that also we have studied earlier, that the direction of dipole moment is from negative charge towards positive charge. Now when this electric dipole is placed in an external uniform electric field, what happens? The force will act on a negative charge, that is on this charge, as well as the force will act on a positive charge. We know that when any charge is placed in an electric field, the force will act. So here we will see individually that if the negative charge is in an electric field, then the force will act in the opposite direction of electric field, and that force is given by Q into E. Here the charge is negative, so the negative sign is there. Similarly, a positive charge, again it is in an electric field, so force will act in the direction of electric field, which is again given by Q into E. So this formula of forces we have studied, that whenever a charged particle is there in an electric field, then the force acts on it. So now the resultant force acting on a dipole F is given by force on a negative charge plus force on a positive charge. But as you can see here, the force on a negative charge is minus QE and the force on a positive charge is plus QE. So if we'll add these two, then the result will be 0, and hence the resultant force on a dipole which is kept in a uniform electric field is 0. But you can see here that these two forces, they are opposite in direction and they are separated by some distance. You can see these two forces, they are separated by some distance, and we know that when the two opposite forces, they are separated by some distance, then the torque will act on it, and due to that torque the dipole will rotate. So here the torque acts on the dipole, and according to definition, the magnitude of torque is nothing but it is force into its perpendicular distance. We have studied about torque in 11th standard. So torque tau is equal to force, which is Q into E, and the perpendicular distance between that two force is 2a sine theta. Now this perpendicular distance is 2a sine theta, that you can see from this figure. You can see here in this figure that this is the direction of the force, and this is a distance between the two charge, which is twice of a. So this distance is nothing but it is the distance between these two perpendicular forces, and here this dipole makes an angle theta, and so this 2a is given, theta angle is given, and so this distance is nothing but it is 2a sine theta. You can see this distance is nothing but it is 2a sine theta, which is nothing but the perpendicular distance, and so we have kept here 2a sine theta. Now simplifying this two, we'll get 2aq e sine theta. You can see here this is 2a, I have kept here QE as it is here, and sine theta. Now we know that 2aq is nothing but it is dipole moment P. So in place of this 2aq, we have kept P. This is E. So P E sine theta. And whenever there is sine theta, we can write that in a cross product way. So here torque tau is nothing but it is P cross E. Once again, this is P, this is E and sine theta. We know that P and E both are vector quantities and they are related by sine theta. So if we'll remove this sine theta, then definitely we have to put a cross product. If there is a cos theta, then we have to put a dot product. So I think you can understand this, that after this step we can write the torque in a cross product way. So definitely this torque is a vector quantity and it must have the direction. So what is the direction of the torque? So direction of torque is perpendicular to the plane of the paper. Perpendicular means normal to the plane of the paper, and it is coming out of it in this situation. This dipole will rotate in this way, and you can use the right hand thumb rule. So its direction can be given as dot because it is coming out of the plane of the paper. Now suppose if this electric dipole is rotating in a clockwise direction, then in that case the direction of torque is perpendicular to the plane but moving inside the plane, and that can be represented by cross. Cross means moving inside the plane of the paper. Now some important points related to this topic. Now here first point, it says that in a uniform electric field force is always zero on a dipole, but torque may or may not be zero. Torque can be zero only if electric field and the dipole moment they are parallel to each other. If they are parallel, then we know that theta is equal to 0, and if theta is 0, then sine 0 is also equal to 0. You can see if this angle theta is 0, then sine 0 is 0, and 0 into anything will be 0. So in that case, when this electric field and a dipole moment they are parallel, then the torque will be 0. Also if they are anti-parallel, when they are anti-parallel, angle theta is equal to 180, and again when the theta is 180, sine 180 is equal to 0, and 0 into anything is 0. So in that case also the torque is 0. Now the second point, in non-uniform electric field. Now see, we obtained the formula for the dipole in a uniform electric field, but here the case is given for non-uniform electric field. In non-uniform electric field, the force acting on a dipole will not be equal to 0. In uniform electric field it was 0 always, but here in non-uniform electric field it is not equal to 0. So some force will act on a dipole, and as the force acts on a dipole, that force will be always in a direction of decreasing electric field. Now let us see how it happens. Non-uniform electric field can be shown in this way. That means the electric field lines, they are not parallel. If they are parallel, then it will be uniform electric field. Now in such type of electric field, if we'll put a dipole, suppose a dipole is placed here, this is positive charge and this is negative charge. So here what happens, the charge which is placed here in a denser electric field will have more force on it. Here the strength of the force will be more, and here this charge is placed in a less denser electric field. So here the force will be less. So if we'll take the resultant force on a dipole, then we'll get some value of force because here it is greater, which was not the case in uniform electric field. We have seen that in uniform electric field, the force on the positive charge and that on the negative charge were equal and opposite, and so they totally cancel out each other. But here the force on this charge will be more compared to this, and so it will have some difference.